What the hell is going on in here?
In a world where hackers are working day and night to infiltrate your network, Jay and Penny are here to talk about it. Welcome to the Order of the Cipher.
Penny, FBI's got you covered. You don't need to do cybersecurity anymore.
They got it all?
They got it all handled.
They're on it?
Yep, they're
Right
on
on.
it. They closed the open shells in Microsoft Exchange on behalf of companies that weren't closing them. They scanned the internet, found open servers that have been broken into, and closed the door.
So are they going to take care of like patching for individual computers now too?
Well, this is opening a big discussion topic about how far is this going to go. It's not unprecedented, actually. There was a botnet called Core Flood that the FBI, this is back in 2011, and the FBI shut that operation down by logging into the machines and closing access for the Core Flood botnet. So it's happened before. There's probably other examples besides that, but this time around, you may recall that Microsoft Exchange server was broadly broken into. It was
it was a big deal.
Big deal.
Big
Everybody
deal.
went scrambling. And I would think that the big lesson there is you should not be running Microsoft Exchange server on your own at this point. Like it's a complex enough, important enough service.
Also, you should be patching it.
Yes. But you suck at it is
Right.
kind of the lesson.
Well,
there.
yeah, everything's complicated.
Yeah. So use Azure. There's many companies that will host Exchange, on your behalf and run it securely. Or you can use Microsoft Azure. You can set it up on some other cloud provider like AWS. Well, people didn't. They forgot about their servers. They forgot about them so much that the FBI couldn't get anyone to respond. So they went to, they got a court order that said, log in to these, well, not log in exactly, but just trigger these machines to close that open port, that open opportunity. And you can notify people later. So for a little over a week, the FBI ran around the internet in the US, closed this vulnerability, and then could notify people later. They did not apply patches. They did not do any scan for further penetration that may have taken place.
Just this one vulnerability then.
Yes. And now the Justice Department is, loudly trumpeting this, what they called a private-public partnership, even though this really is closing a bunch of zombies. They did work with Microsoft to get this issue resolved. Clearly, there was some discussion about what to do with the examples that just we can't reach them, we can't close them. What are we going to do? And this is probably a sign of things to come in situations like this. You just can't have these zombies out there spreading the disease.
Right. And if you have the ability to rectify an issue, then maybe it becomes your responsibility.
Whose responsibility?
Well, the government took responsibility for this, right?
Yeah.
So if there are other vulnerabilities that they can fix, are they going to take responsibility for fixing those?
That's what kind of remains unclear. What is the government's responsibility to the public when there's a broad collection of private companies that are, they're not bad actors, they're
Right.
negligent.
Right.
Yeah.
And maybe they don't have the know-how, maybe they don't have the time, or for whatever reason, they didn't get around to making this change or this fix.
Clearly, from the perspective, I mean, someone is seeing this as the way things should be done, or must be done. Maybe I don't know what all the thinking is within the government that led to this point, but the tone of the press release really is, I mean, the way that they talk about this private-public partnership, they're really strongly implying there's no other way to handle this,
right?
Yeah, and expect it to continue. So I mean, I'm done. I'm just going to rest. I'll let the FBI sort it out.
Right?
Yeah.
Right? Definitely some benefit from there.
Yep.
But then also definitely some questions too.
Mm-hmm. Penny, I've got a value pack for you today on the women in tech.
Oh, nice.
I couldn't just pick one. I picked five.
It's so difficult. Five. Nice.
Now, they all work together.
Okay.
And
they're a team.
Yeah, they...
Do they do volleyball? Oh, no, that's more than five.
I bet one of them somewhere between high school and college did, but they met each other at Penn State, and they've all ended up working at SpaceX.
Ooh, nice.
And Allie, Fawn, Kate, Liz, and Lauren, they call them the PSU group at SpaceX, or at least
Penn State.
The article did to make them,
right.
sound. But they had a few quotes that I thought were kind of neat. I wanted to share. After interning, that's where they really got started, was interning at SpaceX. They had some other internships, and some of them got hired at other companies doing things like manufacturing and lean manufacturing and industrial engineering. So this is, the process of making things. And
right.
Elon's talked about prototypes being easy, but making things is really hard. And so these women are skilled in making things. Well, they got hired by these big conglomerates that wanted to make toothpaste or cereal. Which what
is
they were
important.
Referencing.
I have to have my toothpaste, but yeah.
Yeah. It makes the world go round, but they just couldn't.
Right.
The cutting edge, the excitement, the focus, the energy, they just couldn't get SpaceX out of their heads. And
right.
Went back and applied for open positions. And they had all interned there before and ended up getting jobs there. So they said everything there is fast-paced. There's always a new challenge taking place, and that really motivates them to come to work every day. One of them had a really good piece of advice, which is don't be afraid to apply for a position that is out of your comfort zone. And I couldn't agree more with that.
That's actually very challenging, but good advice, but very challenging.
Before applying, they didn't think that they would ever end up in the aerospace industry.
Right.
And for a long time, that was an industry that seemed pretty stagnant. It did what it did, and there wasn't a lot of change happening, but they've found themselves there and absolutely loving it, and hopefully defining the future of that entire industry.
Now they're on rockets to Mars.
Yeah.
Or working on them.
So congrats to the PSU group at SpaceX.
Very cool. My lady is amazing, also into space, but she is a doctor, a dancer, an author, an actress, and an astronaut.
A doctor, a dancer, an author, an actress, and an astronaut?
Yes. Yes, she is.
What is she going to do when she grows up?
The world is her oyster, apparently.
Wow.
I'm talking about Mae Jemison. She is the first female African-American astronaut. She was part of the Endeavour space trip in 1992.
On the shuttle?
Yeah.
So was there someone that influenced her?
She was heavily influenced as a young child by Nicole Nichols, the actress that played Lieutenant Uhura in Star Trek.
Oh, yeah.
Right? So then after her trip into space, when Star Trek approached her for a role in one of their episodes for Next Generation, she happily agreed. So, astronaut, actress, author. She also spent 2 years as the medical officer in Peace Corps in Africa because she speaks, well, not just because, it's because she's a doctor. It helps that she speaks multiple languages, Swahili, Japanese, Russian.
Whoa.
Right? Additionally, she is involved in several foundations that support science, technology, and social change, including the 100-Year Starship Project, which is through DARPA. And its goal is to have human space travel to other stars within the next 100 years.
Wow. This is amazing.
She is super cool. And icing on the cake, Lego made a little minifigure of her as part of the Women in NASA series.
Wow. That's great.
Yeah, she's cool.
So what motivates, how does she find the time and the energy?
I don't know. Apparently, when she was going to college, she had like 2 major tracks. Well, probably more because she's also an engineer, but she had to decide between being a doctor and being a professional dancer. She chose the doctor route, but she's still involved in choreography and dancing and things like that. So
I want to meet her
her
parents and teachers.
Right? Where does she get the time, the energy? I don't know, but
Your
she's
kid is
absolutely fantastically amazing.
Yeah, your kid is facing a choice between a doctor and professional dancer, and and they didn't just step in and they let that be her decision. That's
they let her do that, which means that she ended up being a doctor and a dancer and an engineer and an author.
Back off a little bit. Look at what you get both.
And an actress. Oh yeah, and an astronaut.
Wow, way to go,
Mae Jemison. Yeah, she's amazing.
Yeah.
So one of the most important, in my opinion, aspects of security is user access. So identity and access management, right? Mm-hmm. Who can do what and what they do, who has done what. AWS has made who can do what easier because it's incredibly complicated. There's 500,000 different things, and can they read, can they write, all of that. We talked earlier about how they've made it easier with the access analyzers. So you give people, some level of permission. You have them do their work. It generates a policy for what they actually need.
Yes.
And then you've been able to scope down their policy.
Yep.
For least privilege, which we all know is the ideal, but actually kind of difficult to get to.
Mm-hmm.
So
Very.
Amazon has made that easier.
Yep.
They are also working on making other aspects of access management easier. Remember a long time ago, we talked about trying to figure out who has done what. We had a discussion about with assuming roles, which is a good way to have users get access, to assume roles rather than give individuals access. But then how do we figure out what that user has done? So what AWS has done has made that entire process super easy. The benefit of this change is that you don't have to go through that great big long process. By setting the source identity attribute, it translates the role that was used to the person or the application that did the thing. So you set that, and then you go to CloudTrail, and based on, you have an action that was done, and you're like, who did this action? You go to CloudTrail, you don't have to translate and look at multiple different logs or do any of that kind of thing.
Yeah.
You just go to CloudTrail. It also works for if a user uses a role to assume another role. It also does that.
No kidding.
Yeah. Right in CloudTrail. It's all right there.
So I assume I'm a developer. I assume a role that my application will take, and it has to assume a role, and I'm all in I'm in the testing world, but this will show me that I, the developer, was the one that assumed the first role and the next role and on and on from there.
Yeah. So it basically correlates an action done by a role to a corporate identity or to an identity.
Yeah, yeah.
Without multiple logs and cross account this or all that other stuff.
And it even works cross account.
Yeah.
That's incredible, because before you would have to correlate the logs from two different accounts and figure out, okay, Penny issued a call to STS in this other account, and
right.
Yeah.
When you were explaining it, I don't remember all the nuts and bolts when we were talking about this ages ago when I was learning, because I come from the Microsoft Active Directory world. So you were explaining to me what is similar and the nuances that are different, which I'm still learning. But you had to correlate this number with that number across multiple logs and then timestamps and things like that. And it was in user administration for Active Directory. You need to know who did what.
Yes.
Right? Well, you need to know that regardless of the platform, but it seemed a whole lot easier in Active Directory. Who did this? Mm-hmm, mm-hmm. All right. I know who did it. But in AWS, then we had to do the this and the that and the other thing to correlate. Well, now that's all done. You set the source identity attribute, and then you go to CloudTrail.
Yeah.
Done.
Great.
Yeah.
The dark side.
Sometime I want to talk to you about Morpheus, this cool chip concept that was put together by a research team. But one of the issues that it mitigates is something that actually had AWS scrambling.
Really?
It had everyone scrambling to fix this. This was a bug that was so insidious. Well, it not a bug, it's an attack. It's not a bug at all. I mean, that's the one of the amazing things about this. This attack was so insidious and so effective, and could have revealed any arbitrary piece of information within a system, even in a shared environment. That's what was so incredible about this. And it's actually a side channel attack, not a direct attack, using Intel's processor against itself. Do we have enough pieces here?
Oh my goodness.
Coming together?
Already I'm a little bit confused, but a little bit excited to figure this out.
It's pretty subtle, and it used speculative execution and branching. So, all right, we're going to try to get through this pretty quickly. For every modern processor to go faster, they will actually guess where the code is going to go next. So there's actually a part of the processor whose job is to make educated guesses about where the program is going over the next dozen or 100 or so instructions.
Okay.
They can, on loading a program, look for jumps. Based on a condition, I'm going to jump to some other part of the program. Now we're talking about machine code, okay? Very low level.
Right.
But there's jumps happening all the time.
Right.
So if I say I want to use Adobe Premiere to do some video editing, all that code to run Adobe Premiere gets loaded, and there's actually a chance while it's being loaded for the computer to analyze the program and to start to make some of these educated guesses. Okay. In fact, to make a computer system feel like it's going even faster, how about I use I've got all these different cores, right? And I've got different subsystems within the cores. How about I use some of this extra transistors that I've got sitting around to go ahead and execute some of the code that I think I'm going to need? And if I don't need it, I just throw the results away. No big deal. But if I was right, then the program runs a little bit faster.
Right,
Feels like
because it's
going
already
faster.
got the thing that it was going to be asked for.
Pre-computed, ready to
Right.
go. Okay.
Yep.
And again, this is happening very, very low level. This is all assembly instructions. This is not happening in any kind of high level language that we might write something in. These are itty bitty little steps. But what we've just described is two different things. One's branch prediction, where we guess about where the program's going to go, and speculative execution, where we just used empty resources that were sitting there anyway to pre-compute things, and then we can appear to the user like things are, well, they are actually going faster. They are truly going faster. Also on modern computer chips is a bunch of security features, especially when we get into virtual machines. In the old day of virtual machines, I had a processor that was imitating itself, and that took a lot of overhead. These days, the processors are designed with virtual machines in mind. So when Amazon, some other cloud provider goes to Intel and says, I'm going to put together a data center. I need 1 million computers, or I need 100,000 cores, chips. Intel is selling them a processor that is absolutely designed to be used in that data center. And one of the things that it includes is a bunch of security that prevents any of the guests from getting access to the lower level system. So you're running a virtual machine, I'm running a virtual machine. Those are both considered guests in the virtual machine world. And I can't see your stuff, and you can't see my stuff, and neither one of us can get down into the low-level guts of the physical hardware that we're actually running on, okay? And the processor actually enforces that on our behalf. However,
there's always a but.
Yes. What if the branch prediction and the speculative execution are allowed to get ahead of the program, and those security features don't get applied until we actually know where we're going? So what that means is there can be code that is executed, and later the processor figures out that I never should have executed that code.
Right, because we ran a different way.
Yes. The system on the chip that's doing the security checking wasn't looking at speculative executed code. So I could have an attacker could write code that they know is going to get branch predicted and they know is going to get speculatively executed before the security system has a chance to actually evaluate it.
So they're actually running something.
Yes. Now, I'm never going to be able to see the results of the computation. That is key to kind of understanding this. This is where we get into, it's not a direct attack, it's a side channel attack. The attacker cannot use this speculative execution to get a peek at the value. But if they do a computation that takes a long time when it's true and is short when it's false,
then they get some kind of information. That's taking a long time, so I know that it's true.
Yes.
That happened like this. I know that whatever that is false. So they're getting some information, just not the result.
Yes. Now, everything, of course, is represented in binary, so I can just run a bunch of tests. I can say things like, is the first character a 3? And then it comes back and it says, go fish. Is it an 8? Is it a this? Is it a that? Well, if you do that in a crafty way, you can basically search and say, is it high? Let's say all the values are between 0 and 255. I've got an 8-bit number. Okay, the first thing I'm going to say is, well, is it lower than 128, I'm going to divide my search space in half and run that calculation and see if it takes a long time or a short time. And that's going to tell me which answer it was. Okay. So you do this with, you have to actually watch the timings. I mean, the code that the attacker is running has a bunch of timing analysis added into it so that they can measure whether it took a long time or a short time. But eventually you can get access to some piece of information. And what are you going to want that to be? You're going to want it to be a key. You're going to want it to be a decryption key, some essential secret piece of info that I can then use to easily break apart everything else that's in memory. So that is the Spectre attack.
To be clear, this side channel Spectre attack made it so that an attacker might potentially be able to breach the host and guest layer?
Yes.
Whoa, that's big.
Yes.
That's huge.
Because in the security section of the chip is what's called bounds checking. That's really where Jay can't access Penny's info and Penny can't access Jay's infos. We have different memory spaces, and if I was to make a request involving your memory, the processor would say, no go, buddy. That's Penny's space.
That's the job of the security portion of the chip.
Yes.
Which in our scenario has not yet been applied because we're doing speculative stuff.
Yes. And the speculative execution, there can be a reference to your information. The speculative execution engine will compute that value. It will check whether your key, your secret key. Because it will just
check all of them.
You get a branch prediction plus speculative. So the branch is so it'll
right. But if I ask enough questions,
yes, if you ask enough questions,
I can ask about your space, and I can ask about my space, and I can ask about Jesse's space, and I can ask about all the different spaces. If I ask enough times, it'll answer all those questions.
For it to be a really valuable attack, I mean, you're after one very specific piece of information.
Right.
Yeah. But eventually, given enough times, you can put it all together. So this got out, and often when there's attacks like this, there's a researcher involved, and they announce that there's this issue, and they say, "Hey, I'm going to publish my findings at this conference that's in, 2 weeks, 2 months, 2 years." Giving you a heads up that I'm going to reveal to the world that this is out there.
So if you want a chance to fix it before everybody else tries to take advantage, jump on it now.
Yeah. Well, this one, they had hardly any time at all. And they had to get this done really, really, really fast.
By they, we're talking about like Amazon and Microsoft and Intel,
yes.
Whomever. They.
Yeah.
The big they.
Mm-hmm. There's a lot of computers that are out there that still suffer from this. I mean, make no mistake. This was not you can't change the code. This is the chip, and the way that it executes, you can't, it's literally in silicon. There's no way to go and change it. Now, they could create some intelligent, kind of like antivirus, kind of, the antivirus is looking at the code in the machine form, which is we're in the same area, we're in the same ballpark here. So right. Antivirus is kind of working the same way, looking at the code in its machine form and looking for signatures that indicate that this is a virus or malware or Trojan or something like that. So similar issue here.
So you can't fix the chip, but you can add software to look for the thing.
I can have the operating system say, do not allow this code to be executed if it meets certain. Now you've got this, a new race going on because people can obfuscate code. You can encrypt code.
Software is buggy.
Yeah, and that too. So
right.
So that's the Spectre attack, side channel attack, and in the future, sometime we'll talk about a chip that was recently produced that is very unique and prevented a ton of the most valuable attacks, which are things like Spectre. So that's called the Mobius chip, and we'll talk about it another time.
Right on.